Hello, calculus students. Welcome to our continuing series on Taylor polynomials. And now I am going to show you how to expand e to the x. And let's use our special point x equals 0. Okay. So recall Taylor polynomial would say that f of x, we'll just call this f of x here, is equal to f prime of a x minus a to the k, the kth derivative of f at a times x minus a to the k divided by k factorial, k from 0 to infinity. And remember, this only works for some functions, but e to the x is one of them. So let's see what happens when we expand e to the x. Well, the first term here we're going to have is e to the 0th, which is just 0, okay, times x to the 0th over 0 factorial, plus the derivative, the first derivative of e to the x, which is just e to the x at 0, times x to the first over 1 factorial, plus the second derivative of e to the x, which is still e to the x, to the 0th, times x squared over 2 factorial, plus the third derivative, which is still e to the x at 0, x cubed over 3 factorial, and so on. So we simplify all this stuff, and we get that this first term here is just 1. This is just x. This is just x squared over 2 factorial. This is x cubed over 3 factorial. And we could keep on going. It's going to be x to the 4th over 4 factorial, and so on. Okay, so e to the x is actually equal to this polynomial here. Okay. And the more terms you add on you have in this, the more it's going to resemble this result, this function here. Okay. Now, let's look at some practical implications first, because those are maybe a little bit more easy to grasp. So if I ask you to integrate this function, sine of x squared dx from 0 to pi, well, there are no basic antiderivatives for this. You have to do some pretty crazy stuff, okay? But we can at least estimate it in this way. So remember that sine, let's not forget that sine of x, or sine of something, of some expression, is really equal to 1 minus that expression cubed over 3 factorial plus that expression to the 5th over 5 factorial minus that expression to the 7th over 7 factorial, and so on. Okay. Well, the particular expression that we're dealing with here is x squared. So we can substitute x squared in here for all of those terms. And this integral is approximately equal to 1 minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial dx. Okay, and it's approximate. So I know that a calculator you can type this into a calculator and figure it out, but this is what the calculator is actually doing. It does this for many, many terms. And you may ask, well, why do I have to do that? Well, if you're studying Calculus 2, there's a good chance you might work in the mathematics field or engineering, where you might have to program some of these things or verify some of them. So this is kind of a rudimentary understanding of how your calculator actually does some of the more complicated integrals. Okay? And if you, again, want more accuracy, well, calculate more terms. Okay, so if you want a better answer to this, well, you calculate some more terms. Okay. So there's some practical applications for you. Before we move on to the theoretical results, I'm going to end this video here and just make one final note, is that note that polynomials, one of the reasons why we like polynomials, are easy to derive, easy to differentiate, okay, and integrate. So integration is usually the tricky part, and it's hard to do, but polynomials, it's very easy to integrate them. So one of the practical applications is that we can use polynomials to calculate integrals that would otherwise be incredibly difficult to figure out on our own. Thank you for watching. Have a wonderful day.